Hello there and welcome back. In the previous two videos, we discovered how to find the moment generating function for the geometric and binomial random variables, and from them we were able to derive the properties, the expected value, or the first moment, the second moment, and the variance of those two random variables. In this video, we'll do a third example of the Poisson distribution. So remember, for the Poisson distribution, the probability mass function is going to be e to the minus lambda times lambda to the x divided by x factorial. So let us now find the moment generating function for it. So the moment generating function, by definition, just recall, is the summation over the support of the probability mass function times e to the tx times the probability mass function. So the domain of the probability mass function for Poisson is the interval 0 to infinity. So this is going to be a summation from x is equal to 0 to positive infinity of e to the tx times e to the minus lambda times lambda to the x, all divided by x factorial. So observe that e to the minus lambda is just a constant, so I can factor that out of the summation. So I have this is e to the minus lambda multiplied by the sum from x is equal to 0 to infinity of e to the tx times lambda to the x, all divided by x factorial. Notice that both of these expressions both have x in the exponent, so we can pretty much factor that out of the exponent and rewrite it in a nicer way. So I can rewrite this as e to the minus lambda times the sum from x is equal to 0 to positive infinity of lambda e to the t, all raised to the x, all divided by x factorial. To observe this next observation, I'm going to let u be equal to lambda e to the t. So once I do that, this is equivalent to writing e to the minus lambda times the sum from x is equal to 0 to infinity of u to the x divided by x factorial. And you should recognize this as the Taylor series for e to the u. So therefore, this is going to be equal to e to the minus lambda multiplied by e to the u, where u is lambda e to the t. These have the same exact basis, so I can combine them. So I can rewrite this as e to the lambda e t plus negative lambda. And moreover, we can factor out a lambda out of both of those expressions to find that this is equal to lambda times e to the t minus 1. So this is the moment generating function for a Poisson random variable. So from it, we're going to derive the first and second moments and derive the variance from them. So the first derivative of this function with respect to t is going to be e to the lambda e to the t minus 1 times the derivative of the exponent, which is going to be lambda e to the t. So therefore, the first derivative of the moment generating function evaluated at 0, which is equivalently equal to the first moment of a random variable, is going to be equal to e times lambda times e to the 0 minus 1 times lambda e to the 0. E to the 0 is just equal to 1. So we have 1 minus 1, which is 0, 0 times lambda, which is 0, and e to the 0, which is equal to 1. So we have 1 times lambda times 1, which is equal to lambda. Therefore, the first moment, or the mean, of a Poisson random variable is just equal to the parameter lambda. Now that we have our first derivative, or our first moment generating function's derivative, now we can find the second. So the second derivative of our moment generating function is just the derivative with respect to t of lambda e to the t times e to the lambda times e to the t minus 1. So I can do a product rule in this expression. So this is going to be equal to the first times the derivative of the second. So it's going to be e lambda e t minus 1 times e, or lambda e t. So first derivative second plus the second times the derivative of the first, which is itself. I'm not going to bother simplifying it because I'm just going to plug in 0 for t anyway. So m double prime of x of t, which is equivalently equal to the second moment of the Poisson random variable, is going to be equal to what? So e to the 0 is equal to 1, so we have lambda times 1, which is lambda, times, so e to the t is going to go to 1. 1 minus 1 is 0, 0 times lambda is 0, e to the 0 is equal to 1. And then we have times lambda e to the t is going to go to 1, so times lambda again. Plus, so where does this go? So again, that goes to 0, that goes to 0, that goes to 1. And then that goes to 0 times lambda, which is lambda, so that gives us that expression. So that means the second derivative of the moment generating function is just equal to lambda squared plus lambda. So this is the second moment of the Poisson random variable. So we've already shown that the first moment of a Poisson random variable is equal to lambda. So from these two things, we can derive the variance of the Poisson distribution. So the variance of any random variable, as we know, is the second moment minus the square of the second moment. So the second moment we've already found to be equal to lambda squared plus lambda. The first moment is lambda, so we just need to square that. So notice that lambda squared is just lambda squared, and lambda squared, its opposite, is located there. So this is just giving us lambda. So that means the variance of x is equal to lambda as well. And this is a very important observation because notice that the mean and the variance are equal to the same exact thing. So therefore, if x is Poisson, then the expected value and the variance are both equal to the parameter lambda. And that's how to generate the moment generating function for the Poisson random variable and use it to calculate the first, second, and variance of the random variable. You can also use it to calculate the third and fourth moments if you wish, but we can leave that to you as an exercise.